Today in this module, we will learn how to use samples from two different populations to infer about the difference, if any, between the parameter values of the two populations. We would also learn how to make inferences about the difference of two population means when the samples are large and when they are small, keeping in mind the form of the population distributions. We would also learn how to make inferences about the difference in proportion of successes of two populations. Although the sample statistics used is the same for estimation and testing, but the value of the test statistic will differ in the two cases. We would also try to understand how to make inferences about the ratio of two population variances. Let us introduce the subject. Inferences about parameters of two populations are basically designed to enable a comparison between two populations with respect to the parameter in focus. Comparisons are often made to establish causality. For example, whether a new technique improves productivity. When making inferences about two populations, samples can be drawn using a randomized controlled experiment based on consciously selected samples that ensures randomness and is designed to be able to control for other factors during the selection process. The other approach to sample selection is retrospective observational study based on historical data that lacks any controls at the time of data collection. We can have more confidence in the results obtained when samples are selected using a randomized controlled experiment. Let's learn about inferences about two population means. So let's assume the means of two populations x and y be denoted by mu x and mu y. The means of the random samples from the corresponding populations can then be denoted by x bar and y bar respectively. The variance of the sampling distributions of x bar will be denoted by sigma x square by m, where sigma x square is the variance of the first population and m is the size of the sample from that population. Similarly, the variance of the sampling distribution of y bar could be denoted as sigma y square upon n, and sigma y square and n are the population variance and sample size respectively in this case. It is reasonable to assume that if population means are unknown, then the population variances will also be unknown and would require to be estimated, let's say, by Sx square and Sy square, where Sx square is written as sigma xi minus x bar square upon m minus 1, and this summation is from 1 to m. Similarly, we define Sy square as sigma yi minus y bar square, where I is from 1 to n divided by n minus 1. Let me repeat, the size of the sample for x is m and the size of the sample for y is n. Let's now understand the estimation of the sum and difference of means. We know that x bar and y bar are the unbiased estimators of mu x and mu y respectively. We can now use this to derive the unbiased point estimators of mu x minus mu y and mu x plus mu y. The expected value of x bar minus y bar is equal to expected value of x bar minus expected value of y bar, which could be denoted as mu x minus mu y. And similarly, expected value of x bar plus y bar is equal to expected value of x bar plus expected value of y bar, and can be written to be equal to mu x plus mu y. So that mu x minus mu y can be estimated by x bar minus y bar, and mu x plus mu y can be estimated by x bar plus y bar. Let us look at the large sample confidence interval for these two population means. To derive confidence intervals for x bar plus minus y bar, we need standard error of the distribution of x bar plus minus y bar, which is denoted as sigma x bar plus minus y bar and is equal to under root of sigma x square by m plus sigma y square by n, which could also be written as under root of sigma x bar square plus sigma y bar square. Under the assumption the two samples are independent and population variances are known. If sigma x square and sigma y square are unknown and estimated from sample data, then the estimated standard error of x bar plus minus y bar is denoted as s x bar plus minus y bar equal to under root of sx square by m plus sy square by n, which again could be written as under root of s square x bar plus sy bar square, assuming independent samples from the two populations. Thus, the sampling distribution of x bar plus minus y bar is centered at mu x plus minus mu y with a standard error which is equal to under root of sigma square x bar plus sigma square y bar, or an estimated standard error of under root of sx bar square plus sy bar square. Now, this result can be extended to the estimation of a sum of more than two population means. The point estimate of sigma mu I is equal to summation xi bar with the standard error of under root of summation sigma xi bar square. The standardized variable z now can be written as, in bracket we can write down x bar plus minus y bar minus, in bracket again, mu x plus minus mu y divided by under root of sigma square x by m plus sigma square y by n distribution, if both populations are normally distributed with known variances. Let me make it very clear, I may be interchangingly using sigma x square or sigma square x as same. Similarly, sigma square y, or sometimes I am using sigma y square, which is same. Now, we can then derive the confidence interval just like in the case of interval estimation for single mean. The 100 into 1 minus alpha percentage confidence interval for mu x minus mu y is obtained as, in bracket, x bar minus y bar minus z alpha by 2 into under root of sigma square x by m plus sigma square y by n, comma, into x bar minus y bar plus z alpha by 2 into under root of sigma square x by m plus sigma square y by n. So, our confidence interval has these two ranges. Similarly, the 100 into 1 minus alpha percentage confidence interval for mu x plus mu y is x bar plus y bar minus z alpha by 2 into under root of sigma square x by m plus sigma square y by n, and x bar plus y bar plus z alpha by 2 into under root of sigma square x by m plus sigma square by n. If either or both populations are not normally distributed, or if variances are unknown, then by central limit theorem, provided samples are sufficiently large, which means m is greater than or equal to 30 and n is also greater than or equal to 30, and if populations are not normal, where m is greater than or equal to 40 and n is also greater than or equal to 40, if variance is unknown, then z could be written as equal to x bar plus minus y bar minus mu x plus minus mu y upon under root of sx square by m plus s square y by n, which will be approximately normally distributed. If population variances are equal, then you will find that sigma 1 square will be equal to sigma 2 square and could be written to be equal to sigma square. And this needs to be estimated using available sample data. So far, we had used s square x and s square y to estimate the two population variances. It is unlikely that although sigma 1 square is equal to sigma 2 square, we will also find sx square is equal to sy square. To arrive at an estimate of the common variance sigma square, we use data from both samples, giving greater weightage to the larger sample as that has more information. We obtain the pooled variance sp square or s square p as a weighted average of s square x and s square y. Thus, sigma hat square is equal to sp square is equal to m minus 1 s square x plus n minus 1 s square y upon m plus n minus 2. If both samples are large, then the 100 into 1 minus alpha percentage confidence interval for mu x plus mu y is written as in bracket x bar plus minus y bar into plus minus z alpha by 2 into under root of s square p by n plus s square p by n. This is equal to, in capital bracket, again in another bracket, x bar plus minus y bar, bracket small close, minus z alpha by 2 into or comma sp into under root of 1 by m plus 1 by n. And x bar plus minus y bar plus z alpha by 2 comma sp under root of 1 by n m plus 1 by n. So this is our expression which gives us confidence interval, and you have two values. So within these two values we have the comma sign showing these distinct values. Let us understand small sample confidence interval for two population means. If both populations are normal with unknown variances and either one or both samples are small, the standardized variable t could be written in this case as x bar plus minus y bar minus mu x plus minus mu y upon under root of s square x by m plus s square y by n. And this will have a t distribution when m is less than 40 or n is less than 40 or both, and unknown population variances are estimated by sx square and sy square. You can observe that if unknown population variances are equal and estimated by the pooled variance sp square, the standardized variable t could be written as sigma or as x bar plus minus y bar minus mu x plus minus mu bar upon sp into under root of 1 by m plus 1 by n, and this also has a t distribution. Basically what we have done is we have taken out sp from the under root sign because of the assumption of the two variances being equal. The degrees of freedom nu of the applicable t distribution will depend on whether the population variances are equal or not equal. Now, s square p has m plus n minus 2 degrees of freedom. This gives the t statistics m plus n minus 2 degrees of freedom. The 100 into 1 minus alpha percentage confidence interval for mu x plus minus mu y when sigma 1 square is equal to sigma 2 square is equal to sigma square is then equal to x bar plus minus y bar minus t alpha by 2 comma nu under root of sp square into 1 by m plus 1 by n, and x bar plus minus y bar plus t alpha by 2 comma mu into under root of s square p into 1 by m plus 1 by n, where this mu or nu is equal to m plus n minus 2. What will happen to the equation or to the formula if the population variances are not equal and samples are small but both populations are normally distributed? In that case, the 100 into 1 minus alpha percentage confidence interval for mu x plus minus mu y could be written as x bar plus minus y bar minus t alpha by 2 into nu under root of sx square by m plus sy square by n, and x bar plus minus y bar plus t alpha by 2 into nu under root of sx square by m plus sy square by n. The degrees of freedom have now got to be equal to, which can be calculated as nu will be less than or equal to s bar or s square x bar plus s square y bar whole square divided by sx bar power 4 upon m minus 1 plus sy bar power 4 upon n minus 1, where we can show that x bar square is equal to sx bar square by m and is equal to sigma xi minus x bar square divided by m minus 1 whole divided by m. And similarly, s square y bar or sy bar square is equal to s square y upon n, which is equal to sigma yi minus y bar whole square divided by n minus 1 and this whole square divided by n. The calculated degrees of freedom is then rounded off to lower integer value for obtaining this nu. For example, if the calculated value is 20.79, the degree of freedom is 20. Let us now try to understand the tests for difference of means. In testing for difference of means, we may like to know if the two population means are equal, or we may wish to test if one mean is greater than the other. The difference in mean values will be denoted by lambda and the null value by lambda 0. If the null hypothesis is h naught denoted as mu x equal to mu y, it can be restated as a null hypothesis h naught, which could be written as mu x minus mu y equal to lambda 0, where lambda 0 is equal to 0. Or we can have a null hypothesis where h naught could be mu x minus mu y and could be written as lambda 0, where lambda 0 is less than or equal to 0, which is a right-tailed test, or lambda 0 is greater than or equal to 0, which is a left-tailed test. In general, we will write null hypothesis as h naught and we would denote it as mu x minus mu y equal to lambda 0. The statement of the alternative hypothesis will indicate if it is a two-tailed test, which means we can write h1 as mu x minus mu y not equal to lambda 0. Or it could be an upper-tailed test. In that case, h1 could be written as mu x minus mu y greater than lambda 0. Or it could be a lower-tailed test, and then we would write alternative hypothesis h1 as equal to mu x minus mu y less than lambda 0, where lambda 0, as we mentioned earlier, is 0, or lambda 0 is less than 0 or lambda 0 is greater than 0. The conditions for using the z-test and the t-test are the same as those for interval estimation. The decision rule using the rejection region approach is the same as that for the single population case. Reject S0 if the calculated value of the test statistic, that is ZC or TC, falls in the rejection region. The table 2 presents the decision rule for the z-test, applicable if both populations are normal with known variances, or if samples are large when population, form, or variances are unknown. For the alpha level test, and null hypothesis H0 can be written as mu x minus mu y is equal to lambda 0. The test statistics is z is equal to x bar minus y bar minus lambda 0 upon SE of x bar minus y bar for large samples, or if population variances are known and both populations are normally distributed. Let me remind you, SE here is nothing but standard error. Now, if both populations are normally distributed but variances are unknown and samples are small, then the test statistics instead of Z is T and is written to be equal to x bar minus y bar minus lambda 0 upon standard error of x bar minus y bar. Now, in addition to the rejection region method, the p-value method can also be applied in tests for difference in means. Once the test statistics has been calculated from the sample data, the procedure for calculating p-value from tail areas is the same as the single sample case. The decision rule also remains unchanged. For significance level alpha, reject the null hypothesis if p-value is less than or equal to alpha. Don't reject hypothesis H0 if p-value is greater than alpha. You can see all these decision rules in table 1. The standard errors SE x bar minus y bar for each type of test is given in table 2, as well as degrees of freedom for the t-test. So you can have a close look at table 2 and see how we have these for population variances. Now, this table 2 is for test for difference in means, the standard error SE x bar minus y bar and degrees of freedom for t-test. Let us now learn about the inferences about difference of proportions for large samples. Let us assume that the proportion of successes in two populations be denoted by P1 and P2. The unbiased estimators of P1 and P2 are respectively P1 hat equal to x by m and P2 hat equal to y by n, where x is the number of successes in the random sample of size m from the first population and y is the number of successes in a sample of size n from the second population. Correspondingly, Q1 hat is equal to 1 minus P1 hat and Q2 hat is equal to 1 minus P2 hat. I am sure you would recollect, we know that P plus Q is equal to 1, where P is the probability of success and Q is the probability of failure. Let us now find out the estimation of the difference in proportions. Now, since P1 hat and P2 hat are unbiased estimators of P1 and P2 respectively, the point estimator of P1 minus P2 is P1 hat minus P2 hat. The estimated standard error of P1 hat minus P2 hat is denoted as under root of P1 hat Q1 hat divided by m plus P2 hat Q2 hat divided by n. Once the point estimate is obtained, we can derive the confidence interval centered at that point estimate. If both samples are large so that NP is greater than 10 and n into 1 minus p is greater than or equal to 10 for each sample, but samples are small relative to the size n of each population, where small n is less than or equal to 0.05 capital N, which is nothing but the size of the population, then the estimator P1 hat minus P2 hat has an approximately normal distribution. Then the 100 into 1 minus alpha % confidence interval of the parameter P1 minus P2 is P1 hat minus P2 hat plus minus Z alpha by 2 into under root of P1 hat Q1 hat divided by m plus P2 hat Q2 hat divided by n. Or it could also be written as P1 hat minus P2 hat minus Z alpha by 2 into S P1 hat minus P2 hat. This P1 hat P2 hat is in the subscript, which means we are talking about the standard deviation of or the standard error of P1 hat and P2 hat. And the second value, which is the other extreme upper value, is P1 hat minus P2 hat plus Z alpha by 2 into S P1 hat minus P2 hat, where S P1 hat minus P2 hat is equal to under root of P1 hat Q1 hat by m plus P2 hat Q2 hat by n. Now this confidence interval is based on the traditional formula for the single population case. The actual confidence level may differ greatly from the specified level indicated by the selected critical values plus minus Z alpha by 2. Now this problem can be addressed by adding one success and one failure to each sample so that sample sizes are m plus 2 and n plus 2. We can then substitute P1 hat and Q1 hat by P1 tilde equal to x plus 1 by m plus 2 and P2 tilde is equal to y plus 1 upon n plus 2 in the traditional formula for the confidence interval. Let us now discuss the tests for difference in proportions. The standard error of the sampling distribution of the difference in proportions requires the use of population parameters. The approach to testing hypothesis is to assume that the null hypothesis is the true until proven otherwise. Hence, we use the null values of population proportions in estimating the standard error. We will discuss here the null hypothesis that the two population proportions are equal. Let's denote the null hypothesis H0 as P1 equal to P2, or HA is which could be P1 minus P2 is equal to 0, which is the alternative way of writing the same null hypothesis. This is versus the alternative null hypothesis H1 equal to P1 minus P2 greater than 0 or P1 minus P2 less than 0, or we may also write P1 minus P2 not equal to 0 for our usual upper, lower and two-tailed tests respectively. Assuming both samples are large and samples are small relative to population sizes, the jet test can be used. The estimated standard error of P1 hat minus P2 hat is calculated under the assumption that P1 is equal to P2 is equal to P. This is done by pooling the data from the two samples. And in that case, P hat will be equal to x plus y upon m plus n, which is same as mp1 hat plus np2 hat upon m plus n, and q hat would again be equal to 1 minus p hat. The estimated standard error in this case is equal to sp1 hat minus p2 hat is equal to under root of p hat q hat into 1 by m plus 1 by n. The test statistics is then equal to z is equal to p1 hat minus p2 hat minus 0 upon under root of p hat q hat into 1 by m plus 1 by n, since the null value is 0. Now, once these samples are observed and the test statistic is calculated, then both the rejection reason approach and the p-value method can be used to reach a conclusion. The procedure is the same as for the large sample tests for means. If the calculated value ZC lies in the critical region in the tail area or areas of the Z distribution, as defined by the type of the test and the alpha level of significance, then S0 is rejected and not rejected otherwise. Similarly, if p-value is less than or equal to alpha, H0 is rejected and not rejected if p-value is greater than alpha. Let us now move on and try to understand about the inferences about two population variances. Now, inferences about two population variances require that both populations are normally distributed. Let the two populations have variances sigma 1 square and sigma 2 square. Independent samples of sizes m and n from the two populations will have sample variances S1 square and S2 square having chi-square distributions with respective degrees of freedom nu1 equal to m minus 1 and nu2 equal to n minus 1. Inferences about the ratio of two population variances, that is sigma 1 square upon sigma 2 square, require the F distribution. The F distribution is a family of distributions with two parameters nu1 and nu2, where nu1 and nu2 are respectively the degrees of freedom of the numerator and the denominator. A random variable that has an F distribution must always have a non-negative value. The distribution itself is positively skewed, and figure 1 illustrates F nu1 nu2 distribution, where we have the F density on the y-axis and we have the F value on the x-axis. We can see the upper tail and the lower tail of this distribution. So the figure 1 shows upper tail and lower tail areas under the F curve with degrees of freedom nu1 and nu2. The critical values of the F distribution are tabled only for upper tail areas for alpha values which are 0.10, 0.05, 0.01 and 0.001. However, we can use a property of the F distribution to derive the critical values in the lower tail areas. That property is that F1 minus alpha of nu1 nu2 is equal to 1 upon F alpha nu2 nu1, where the denominator on the right hand side can be found in the tables for given alpha values. The numerator degrees of freedom are nu2 and denominator degrees of freedom are nu1 on the right hand side of this expression. So if x1 and x2 are two independent random variables having chi-square distributions with degrees of freedom say nu1 and nu2 respectively, then the ratio x1 upon nu1 divided by x2 upon nu2 has an F distribution with the nu1 and nu2 degrees of freedom. Substituting this x1, in fact this is chi1, and substituting chi1 equal to m minus 1 into s1 square upon sigma 1 square, and chi2 equal to n minus 1 s2 square upon sigma 2 square. In the above ratio, with nu 1 equal to m minus 1 and nu 2 equal to n minus 1, we obtain the statistic s1 square upon sigma 1 square divided by s2 square upon sigma 2 square. This ratio has an F distribution with degrees of freedom nu 1 equal to m minus 1 and mu 2 equal to n minus 1. The point estimate of the ratio sigma 1 square upon sigma 2 square is the ratio s1 square upon s2 square. To obtain the interval estimate, we see that probability f1 minus alpha by 2 nu 1 nu 2 is less than s1 square by sigma 1 square upon s2 square by sigma 2 square must be less than f alpha by 2 nu 1 nu 2, and this is equal to 1 minus alpha, which implies that 100 into 1 minus alpha percentage of confidence interval for sigma 1 square by sigma 2 square is equal to 1 upon f alpha by 2 nu 1 nu 2 into s1 square by s2 square, and 1 upon f 1 minus alpha 2 nu 1 nu 2 into s1 square upon s2 square. Or it can be rewritten as 1 upon f alpha by 2 nu 1 nu 2 into s1 square upon s2 square, comma, and f alpha by 2 nu 1 nu 2 into s1 square upon s2 square after rearrangement of terms in the probability statement. The lower and upper limits of the confidence interval for the ratio of population standard deviations sigma 1 by sigma 2 is obtained by taking the square root of the limits of confidence interval for ratio of variances. The usual tests for ratio of variances involve a test for equal population variances. The null hypothesis is thus written as h naught equal to sigma 1 square equal to sigma 2 square, or h naught can be written as sigma 1 square upon sigma 2 square equal to 1. Under the assumption that the null hypothesis is true until proven otherwise by sample data, the test statistics is f equal to s1 square upon s2 square by substituting sigma 1 square upon sigma 2 square equal to 1 in the formula for the f statistics. We obtain s1 square by sigma 1 square upon s2 square by sigma 2 square. The test statistics is distributed with the numerator degrees of freedom m minus 1 and denominator degrees of freedom n minus 1 for sample sizes m and n respectively from the first and second populations. The null hypothesis is rejected if the calculated value of the test statistic, that is FC, is significantly different from 1. The table 3 gives the rejection reason for different alternative hypotheses, and you can see these decision rules for the ratio of variances in this table. The critical values are tabled for alpha levels, which are 0.10, 10%, 0.055%, 0.011%, and 0.001. The one-tailed test can therefore be performed at these levels of significance. The level of significance at which the two-tailed test can be performed are 0.20, 0.10, 0.02, and 0.002. Let us now summarize what we have learned in this module. We have learned that when parameters to be estimated or tested involve more than one population, say for example 2 populations, then we need to consider samples from both populations along with the form of both populations and the respective sample sizes. We have also learned that in driving confidence intervals, we have to first specify the level of confidence and consider the sampling distribution of the estimator to arrive at the confidence limits. We have learned that in hypothesis testing, we initially assume the null value is true until the sample data strongly favors the alternative and we reject the initial or claimed value. We have also discussed that the rejection reason in tests of hypothesis and the confidence interval are disjoint sets, where the level of confidence and the significance level of the test sum to 1. We have also understood that an alternative to the rejection reason method is the p-value method. In the end, we have learned that the estimates or tests illustrated in this module involve the z, t, chi-square and f distribution.